In this question, we're going to graph the curve y equals x cubed minus 7x squared plus 15x minus 9. Well, one of the first things we want to do is figure out where our y-intercept is. So we let x equal 0, we see y equals negative 9. We've got a y-intercept at 0, negative 9. Now we want to know where our x-intercepts are. So we set f of x equal to 0, and we solve. Well, setting a cubic expression equal to 0 means we'll probably have to use the factor theorem. Letting x equal 1 gives us a 0 value for y, so we know x minus 1 is a factor. Dividing x minus 1 into the expression for y, we get x squared minus 6x plus 9 as the quotient. That means f of x is equal to x minus 1 times x squared minus 6x plus 9, which is the same as x minus 1 times x minus 3 squared. Setting y equal to 0 means x is 1 or 3. So these are our two x-intercepts. Now, we know our first derivative is equal to 3x squared minus 14x plus 15 using the power rule. Factoring that, we get this expression here. That means the first derivative equals 0 when x equals 5/3 or when x equals 3. Our second derivative is equal to 6x minus 14. Our second derivative equals 0 when 6x equals 14, or in other words, when x equals 7/3. So we can set our first derivative up here and our second derivative here, and we'll do our interval testing. Well, to the left of 5/3, both of these quantities are negative, making y prime positive. In between 5/3 and 3, this is positive, this is negative, and beyond 3, they're both positive. To the left of 7/3, this is a negative quantity, and to the right of 7/3, this is a positive quantity. Okay, so what that tells us is that at x equals 5/3, we're going to have a maximum. We know we have a maximum because we're going from increasing to decreasing. Another way of knowing that is to say at x equals 5/3, the first derivative is 0 and the second derivative is negative, meaning we're concave down, meaning we're at a maximum. We know we have a minimum at x equals 3 because when x is equal to 3, we go from decreasing to increasing. Another way of knowing that is to know that we have a 0 derivative at x equals 3 within a concave up section, meaning we have a minimum. At x equals 5/3, y is equal to 32 over 27, and at x equals 3, y is equal to 0. So these are our points that we're going to make sure to graph. But we should also figure out the y value where the second derivative equals 0. That's at x equals 7/3. Setting x equal to 7/3, we get y equaling 16/27. That means we have a point of inflection at 7/3 and 16/27. Putting everything together, we have this data sheet for the curve that we're going to want to draw. We know our y-intercept, our x-intercepts, our max point. It's approximately 1.7, 1.2. We don't put that down on a test, or we don't state that those are the coordinates, but it's helpful to know that for graphing purposes. We have a point of inflection at this point here. For graphing purposes, that's approximately 2.3 and 0.6. And we know our increasing and decreasing in concavity drama by looking at this chart here. So now we're going to do our best to graph it. We plot the point 0, negative 9. We plot the x-intercepts of 1, 0, and 3, 0. We know this will be a minimum. We have a minimum point at 3, 0, like we said. Our point of inflection at 7/3, 16/27 is right here. At that point, we want to see that we go from a curve that is concave down to a curve that's concave up. So what we're going to do, I'm going to start here. I'm going to draw a curve that's concave up to the left of 7/3, like I was supposed to, according to this. Okay? Now, to every point here, the tangent line is below the curve. But I'm going into a concave down situation, so if I do a good job of graphing it, this point that was originally pink should be the dividing line between where a curve is concave down and concave up. In other words, from where the tangent line is above the curve to where the tangent line is below the curve. And then I cut through here, and I do my best to make this curve hit the appropriate y-intercept. And if that looks like a point of inflection to you, I'd say that we've done a pretty good job of graphing this curve.